More than 20 years ago, a team at Brookhaven National Lab detected a missing piece in the standard model. A measurement they had taken to better understand the effects of the forces that shape our universe was off. So the international physics community came up with a plan. Take the measurement again with much more powerful instruments and see what sticks. Fast forward to April 7th, 2021, that highly anticipated measurement is finally in, and it seems like the Brookhaven results weren't a fluke. This means that our current understanding of the universe may not account for every particle and force within it, and therefore may need to be entirely reworked.
So this experiment is looking at little elementary particles called muons. And what we really care about muons for this experiment is that they're like little spinning tops. They're like little magnets.
As it turns out, muons are one of the most precise ways for scientists to probe the quantum world. The muon is one of 12 elementary particles described by the standard model. This model aims to understand how each of these particles is affected by the universe's four known forces: the strong, weak, gravitational, and electromagnetic. These 12 particles are divided into quarks and leptons, which are each further divided into 6 distinct flavors. Like electrons, muons are just one flavor of leptons. They also spin like a top and have a negative charge, meaning they're able to generate their own magnetic field. So when a muon's internal magnet is exposed to a strong external magnetic field, like one produced by, say, a particle accelerator, the muon starts to wobble. The rate of this wobble is what physicists call its G factor, or magnetic moment.
This is an experiment that allows us to see from the wobble of the muons what's otherwise an invisible quantum world that contains all kinds of stuff that we'd like to know about.
So it's basically potentially pointing us to something that we don't understand. And this is why it's very interesting.
Muons are around 200 times heavier than electrons, which means the moment they become magnetic is 200 times smaller, and therefore way more sensitive to all of the virtual particles swimming around in the quantum realm. So to measure this moment, precision is everything, which is exactly what physicists from around the world have been after. Which brings us back to the Brookhaven experiment. In 2001, the team published some surprising findings. Their measurement of the muon's G factor deviated from the standard model's prediction, and nothing could account for the difference. Instead of finding a G factor slightly above 2, as the standard model had predicted, they found a G factor that was off by nearly 3 standard deviations.
The Brookhaven experiment was a big surprise. It made a lot of people think that maybe there's something we really don't understand, either about particle physics or about how to do these kinds of experiments.
So the physics community decided that the only way to confirm these findings was to take that measurement again. Led by Fermilab, the Muon G2 experiment cast its first beam of particles back in 2017 and has been searching for the muon's G factor ever since.
We decided to combine the experimental technique by moving the magnetic ring from Brookhaven National Lab all the way to Fermilab.
Fermilab's accelerators first blast particles into a giant ring where they decay into muons. These muons then travel to a second ring where they spin and start to wobble in reaction to the ring's powerful magnets. By comparing measurements of this wobble with the ring's magnetic field, the team is able to walk away with a measurement of the magnetic moment, with a precision of 0.14 parts per million. At this level of precision, we get a window into the world of muons that we've never had before, and a more specific number to compare our theoretical predictions with.
It's taken 20 years of effort by theorists like me to actually make these very, very precise predictions that we're checking. And it's the difference between that theory prediction and what the experiment sees that could be something new, some new force of nature or something that we just didn't know about.
But after years of intense efforts on the part of the team and the muon beam, the first round of results are finally ready.
So the new measurement agrees amazingly well with the Brookhaven measurement from 20 years ago. And the fact that now you have 2 different experiments, including this much more modern version of the experiment, getting the same answer, to me says that the experiments are probably right. And this is the kind of breakthrough that you live for when you're doing science.
The team still has to analyze more data from this experiment, so there's a chance that they'd stumble on some answers in those numbers. But one thing is for sure, the team's search for muon's magnetic moment definitely isn't over.
To me, what's exciting is that we don't know what it is that they're seeing, but whatever it is, it would have to be something fundamentally new. It's not just a little bit different. It would be something that I think would revolutionize our thinking, whatever it turns out to be.
We've actually covered Fermilab's work on the channel before. Check out that video here. Let us know what you think is lurking out there in the universe that could explain the G2's latest findings. And make sure to subscribe to Seeker to hopefully one day find out. Thank you so much for watching, and I'll see you next time.